All right. Well, what we're going to do is we're going to do another problem. This is dealing with Descartes' volume of Descartes, which is this little implicit equation right here. We're not going to find what the slope of the volume is at these different various points. All right, that's pretty easy. We're going to do something a little bit harder. What a lot of people have is we want to figure out where are there horizontal tangents, all right, besides the origin on this volume. All right, and then what we're going to do is we're going to figure out where are there vertical tangents. All right, where do we have a vertical tangent on this volume as well? Okay, and so to do that, we have to understand how to find vertical and horizontal tangents. So let's talk about horizontal. All right, horizontal tangents are where we know that the derivative equals 0. Okay, and so when we have a derivative when it equals 0, that's where we find horizontal tangents. Well, also we can find vertical tangents. That is where the derivative is undefined. That's when we have vertical tangents, because there is no slope. So how do we do that? Well, the first thing is we need to do is we need to figure out the derivative. So we're going to take this equation, volume of Descartes, and we're going to find this derivative. So we're going to take the derivative of this, x cubed plus y cubed minus 9xy equaling 0. Okay? And so we're going to do this, and we have 3x squared plus 3y squared. Don't forget the y prime. And we have to use a product rule right here, and I'm running out of room, so I'm going to just erase some of this right here. Okay. Minus 9y minus 9x, a y prime, and that's going to equal 0. So make sure we use product rule here. Don't forget that. Okay. Now from here, we're going to solve for y prime. All right, we're going to solve for y prime in this one. When we solve for y prime, we can take and move, all right, this little negative 3x squared to the other side. We'll also add 9y to the other side right there. We then have these two expressions left over. We'll factor out this good old y prime. And what do we have left over? We have a 3x squared, and we'll have a negative 9x. Beautiful. We're going to get y prime by itself now, and so we're going to have negative 3x squared plus 9y all over, all right, 3x squared minus 9x. All right, cool. With that information now, I'm just going to draw my little box around here. With that information now, we're going to find out the horizontal tangents. Well, given y prime equals 0, and given that we have a rational function, we're going to look at the numerator. It's when the numerator equals 0. So in this problem, we're going to take negative 3x squared plus 9y, and we're going to set that equal to 0. In the same manner over here, vertical tangents. Well, vertical tangents are defined when the denominator equals 0. Well, what's the denominator? Well, this is going to be 3x squared minus 9. Oops, did I do this right? Oops, this should be y. Should be y right there. I apologize. All right, that should be y as well. I almost messed up, so I apologize for that. All right, and y's, and so we have y and then minus 9x. Okay, and that's going to set that equal to 0. Now you notice that on both of these, in this particular problem, that these values are pretty much the same, just kind of mixed around just a little bit. All right, so we're going to use that information, and we're going to solve for one of these values. So we're going to, in this case, I'm going to solve for y. And so what we have is 3x squared divided by 9, and that's going to equal y, which is really going to have us have x squared over 3. Over here, what I'm going to do very, very similar. I'm going to take this and we have negative 3y squared equals negative 9x. I'm going to divide by negative 9, so we have, all right, once again, y squared over 3. Okay, so very, very similar, very similar. Actually, it's almost the same equation, except all of our x and y's are flipped around. Now, the question is, we have to figure out where these horizontal tangents are. So we're looking for where. Now, when we have a where question, That means we're looking for points. Points of intersection. All right. Basically, we're going to take this equation, all right, that we have for our horizontal tangents, and we're going to figure out where are the points of intersection, where do they have common points with this curve. Now, in order to solve that, all right, we've done this before in some other problems, but we need to then solve the system. Solve the system by using a little substitution. How? Use substitution. So we're going to take this y equaling x squared over 3, and we're going to plug it for every single y value here. So what we're going to do right here is we're going to change the color. I'm going to have x cubed, make sure I plug in everything in correctly, x cubed plus, we're going to have this quantity, all right, x squared over 3, and we're going to cube it. And then I have minus 9x. I'm going to take this right here. That's x squared over 3. Plug that in for that y right there. And set that equals 0. All right, now I'm going to do some algebra. We're going to solve this puppy and find out what we get here. All right, and so we have here is x cubed. We'll have plus, it's going to turn x to 6. We'll have a good old 27 in the bottom there. We'll have minus, this 3 will cancel out, minus 3x cubed. All right, that equals 0. We'll combine those right like terms right there. So we have negative, all right, negative 2x cubed, all right, plus x to the 6th over 27, and that equals 0. Okay. Now, as you can see right here, one of these things is just like the other. What can we factor out? Well, we can factor out a x cubed. When we do that, all right, we'll have negative 2 left over. We'll have a plus, all right, x to the 3rd over 27 right there. And so that equals 0. Well, right here, x cubed equals 0 at 0. Okay, so we have that one. So x can equal 0. But now we're going to solve this one. So find our other x. We're going to have negative 2 plus x cubed, all right, over 27. And that equals 0 right there. So we're going to solve this puppy I'm going to add 2 to the other side. All right, multiply that by 27, and that equals x cubed. And now I'm going to take the cube root of this. So when I take the cube root of 2 times 27, well, the cube root of 2 says the cube root of 2, but the cube root of 27 is 3. So 3 times the cube root of 2. That's what our x value is. So this intersects at 3, all right, times the cube root of 2. And what is our other value going to be? Well, we can find the other value by plugging this value in here. And I'll just plug it right there because that's what the x value is going to be. That's one of our values there. And so we have our y value. So our point is, this is our first point. And our other point is going to be, all right, that's x cubed over 3. So we have 3 cube roots of 2. All right. That's going to be squared, all right, over 3. So what we have then right here is this going to be turned to 9. 9 divided by 3 is 3. All right, 3. And then we have 2 times 2, all right, to the 2/3 power. Okay, so we have that. So this is kind of weird expression right there, but that's what we have. Okay, well, kind of doing the same thing, all right, except now we're going to be putting in y squared over 3, and for all x values. And so this is the point where we have at 0, 0. So it says right here, at what point other than the origin does the formula have this horizontal tangent? All right, then it says find the point A and where the formula has a vertical tangent. Okay, so kind of going through the same process. So we found our one point right here, besides the 0, 0, which we got for that. All right, y equaling 0, 0. All right, so y equals 0, 0, and this point. And for our last one is now we're going to do the same thing, but now with this point right there. So where is this point of intersection? Well, now we're going to use this and plug it in. And what you notice, what you should notice, all right, is essentially it's the same algebraic expression that we had before. We have the y cubed, we'll have the minus 9, we'll we'll have the times y squared over 3 times y, and that equals 0. Everything is the same. Everything is the same, except now it's in terms of y. And so if you look at this, you see that, yeah, that is pretty much the same. And so what we actually have here is going to be negative 2x cubed plus x to the 6th over 27 equals 0. And so what we have right here is we can factor out the x cubed right there. And once again, we have negative, which that's an x, this would be y, I apologize. Y. We have to talk about y's here. All right, we'll have negative 2 plus y to the 3rd over 27 equals 0. And we realize we get to the same values. All right, it's y. So y is going to equal 0. So that means that x is going to equal 0 as well. So we have another point right here of 0, 0, the origin. So I guess that's where the vertical tangent line is as well. All right, and all right, when we have this, there is another point, and what is y going to equal? Well, we know x equals that, so I guess I know that y, when I solve it, is going to equal, all right, 3 times the cube root of 2. And my x value, in this case, all right, is going to be, all right, 3 times 2 to the 2/3 power. All right, so I have this kind of reciprocal, or all right, flip-flop of our value right here. That would be reciprocal, but we have that. So you can see they're very, very similar, but our x's and our y's are going to be flipped around. And that's pretty cool. All right, and so that's how we find horizontal tangents. We set the derivative equal to 0. Sometimes when you solve for just the equation, you have to substitute back in there to find the intersection by using substitution, solve the system. We also have vertical tangents. Vertical tangents are when the y prime is undefined. When you have a rational function like so, you need to make sure that you take the new denominator set equal to 0 and then solve. And if you have to, plug that back into the original equation, all right, to solve for that as well. All right. Well, I hope this helps you out on solving systems or using systems to help you solve for horizontal tangents and vertical tangents and implicit differentiation problems. Good luck and God bless in your rest of your problems.